In this video, I will answer the perpetual question why you can't shave with an axe, no matter how sharp. Or to reframe the same issue inversely, why you can't split fire logs with a razor. And not surprisingly with me, the answer will have everything to do with geometry. So let's take a look at what these tools can and can't do, and it is in this deliberate misproportion comparison where the results to the question are most observable. So actually, let's start with shaving. Let's try to shave with an axe, and here you can see and verify that I try to shave some hairs off and there's nothing here as a result of it. You can also see the edge is not entirely beautiful on this splitting axe. However, it did split some wood for me. Let's verify that the razor blade is sharp indeed and see if we can shave with it dry. And yes, indeed, we can see that there is some hairs that I cut off. So this blade is able to sever some hairs. Let's see what I did with this piece of wood here. I split some of it off here, and I also split a wedge off of this side, which is kind of somewhat nailed back together. I want to show you here the splitting action, how this actually happens, because the razor blade isn't quite observable when it severs hair. This one shows much better. So a splitting action starts with the edge of the tool contacting the wood there to be split. However, the initial sharpness of the edge is inconsequential and absolutely doesn't matter for the success of the splitting, because as soon as the edge of the tool penetrates about 1/1000th of an inch depth or so, which is let's call it half a millimeter, okay, or 1/10th of a millimeter, and this is why I nailed the wedge back on a little bit. You can see that as soon as the edge is in the wood, the actual edge of the tool is not even in contact with the wood anymore. It is the cheeks on the splitting axe that do the prying action that will do the splitting for you. That's why it doesn't matter how sharp this axe really is for splitting. It does a wonderful job because of its geometry. And the same geometry, what makes the razor blade work, is observable on the razor blade, but I would need a microscope for that. However, I can draw. You notice that on a razor blade, the blade contains two parallel surfaces which taper off at the end, something like that, and an edge is formed at this point. There is an included angle here. This is razor, and here is a bevel face, and here is another bevel face on the tool, and it's got two parallel faces, whereas the axe looks somewhat like it's got an edge there and a bevel face there and another bevel face there, and then from then on the tool kind of continues, but the face of the tool is not parallel. Let's see, something like that. And the wood piece again was something like that, and it was pried apart like so, without the edge in contact with the wood. We have the same included angle here, not the same, but similarly we have an included angle here, and this is splitting axe, bevel face, bevel face. So why you really can't shave with an axe has to do not with the keenness of an edge or its sharpness or its fine hone or its mirror polish. It's got to do something with the design of the blade itself, not only the edge. That's why being sharp for a tool to be sharp is not enough. It also has to have the correct geometry in it to be able to perform the cutting action or splitting action or whatever the tool was actually designed for. So, and this concept is called, in terms of tool technology, is called the grind. The tool has to have a proper grind. If it needs to have parallel faces, it's got to have parallel faces. Now, if it's got to have tapered faces, it's got to have tapered faces. Now, in terms of resharpening and honing and maintaining tools, what is this geometry that needs to be maintained and preserved to make a tool effective? Let's try to look at some of these numbers and try to quantify some of these amounts. And we're going to come back to these included angles in a minute, but before we do that, one more thing. Not only the body of the blade that's important, but also something between the edge and the body of the blade. There's one more feature that shouldn't be missed. It is the bevel. And the angle that the two bevel faces include. So we're going to look at this bevel configuration and geometry, and we're going to put some numbers on it. But because these blades are a little more complicated to calculate, I'm going to start off with something simpler. What I have here is simpler tools. This one, this one, this one, and this one. Just give me a sec here, folks. These chisels, and this is a plain blade, are simpler to calculate, and they are also edgy tools. But the blade is simpler because it only has one bevel on it. Here, one bevel, and maybe this way so the camera can focus. It's got one bevel on it, and the underside is totally flat. The blade is also slightly tapering, thicker here than here, but it's only got one bevel on it. And when I put these side by side, do notice that, let me just grab this knife here that's going to be featured later, that this bevel, the length of this bevel on this first tool is the longest. On the second tool, the length of the bevel is shorter. On the third tool, it's even shorter, and the length of the bevel is shortest on this last tool. All of these edges are straight, all of these edges are sharp, but the blades perform massively differently. You may be able to cut hair with this one, not so much with this one, and absolutely forget about it with this one. And why is that? Let me just put these away. And to determine this included angle that is formed between the face, this actually is the face of a chisel, and this bevel angle, you can do it two ways. You can have this bevel gauge which has numbers on it, 20 degrees, 15 degrees, 45 degrees, and you can try to match it up with one of them, and when it's matched up properly, the one side of the bevel gauge or bevel notch is tight against the blade, and the other side, the bevel face here, could be tight or could have a gap in it. Like here we have a gap. The bevel gauge and the bevel are in contact somewhere there, and then we have a gap there. So the blade, this blade has a bevel of a little less than 30, sorry, that's number 20 degrees. Let's try 25. Yeah, 25 is a mismatch as well, but now we have a point of contact here. So the bevel on this one is between 20 and 25 degrees, and the same applies to the rest of my chisels. This bevel gauge is limited, but leads in a different or a definite direction as to determining why you can't really shave with an axe. So this is one of my chisels with an extreme acute angle on it, and with a long bevel. My next chisel was, I'll try to make a nice drawing. Let me see, that was the first, was looking something like that, and that it had a shorter bevel, and it had a greater angle, a greater included angle here that's formed between the face and the bevel. My third chisel was, that one is there, and this one has to be a little steeper. My third chisel might look like, or might be represented like so, included angle there, and the length of the bevel there, and the fourth one could be something like that. Okay, an even shorter bevel, and yeah, that's definitely steeper, and an even greater included angle. Now, on a single bevel tool, on these chisels and plane blades, you can see that as the length of the bevel decreases, the included angle increases, and we can calculate it. We are not only we are not limited by any means by the limits of a bevel gauge, and for this I'm gonna take two measurements. Please recall that in high school, in trigonometry, a right angle triangle was used to illustrate the one of the trigonometric functions. The sine of an angle was calculated by dividing, sine of an angle was calculated by dividing the length of the opposite side by the length of the hypotenuse. This hypotenuse, in our case, is the length of the bevel face here, and the opposite side, the side opposing the bevel angle or included angle, will be measured here on a chisel, like so. I'll show you what I mean. First we need a scientific calculator, then I need my measuring tool, needs to be switched on, and let's grab this chisel. First I'm gonna measure the, let me see, 0, 0, 0, good. I'm gonna measure the length of the bevel, and it is, I'm turning it to capture light in a way you can see where the claws of the calipers are, so everything is in the picture at the same time. Something like that would work. Maybe a little less, thereabouts, 11.9 millimeters. Maybe just give me a sec. Maybe there. The length of the bevel, 11.36 millimeters. Let's go with that. And so this one is length of the bevel, 11.36 millimeters there. And I'm gonna take a second measurement there. Since this blade is tapered, I'm gonna have to be really careful to measure the thickness of the blade only at the top of the bevel. So for that, this part of the caliper here, that is against the face of the chisel, has to be really tight and not rocking. Just try to hold it so you can see it. It's good there. It's good there. There, let's take a reading, 4.16. Okay, let's work with 4.16 millimeters. 4.16 millimeters. Okay, and to calculate an angle, we're gonna need to use the second function sine button. So we're gonna need second function sine, bracket, because we're gonna need an angle. 4.16 divided by 11.36. 4.16 divided by 11.36. Maybe close the bracket, but it's not necessary on this model. There we have ourselves 21.5 degree angle. I just rounded it up slightly. 21.5 degree angle on this chisel, and that's exactly what we verified with this bevel gauge, that it was neither 20 nor 25. And so there it is. This one is 21 degree, has a 21 degree angle. Now let me go back to trying to cut hair with a chisel. Just like you can't cut hair with an axe, you may or may not be able to cut hair with a chisel, and this really has a nice mirror polish on it, you can see. Let's see if it cuts hair at all. Not really. Nah, maybe it cut one little hair there. Okay, so that's that. Oh, you should be storing your chisels bevel down so that the edge is not in contact with the surface upon which the chisel is resting, so it doesn't get dull. So that chisel is sharp and is able to cut hair to some degree, but the rest of my chisel blades here have increasing angles, and I took my measurements, and this was 21.5. My next chisel is about 30 degrees. This one is about 35, and I made this one about 40 degrees because in use, when I notice that a blade fails, there's my ruler here. I'm going to show you this one. When I notice that a certain steepness or a certain included angle given between the face of the tool and the bevel, when the blade fails, it's got microscopic amounts of metal displaced at the end, either bent up or bent down. And it is because the blade is forced through material that makes the blade here at this point too thin, and the metal fails and bends and buckles. If it's forced through a material through which this bevel angle is not designed to go through, the metal will fail. And this is how it looks like on this kitchen knife here. Let me just point at it. Just wait for the camera to focus. You can see failing and buckling metal here, 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 here. Along its edge you can see where it's reflecting light differently, here, at that point, at the next one, at the next one. On the other side it's serrated and also scalloped out, so the deep point in the scalloped blade, the metal fails and folds. So there you can see all the way to the tip of it. Wherever I cut into a chicken bone or whatever I'm slicing, the metal fails. And it has nothing to do with sharpness. It has nothing to do with, or not a lot to do with the hardness of the blade or the material of the blade. It has everything to do with this included angle on the blade. If the metal fails, you have to make this portion thicker, and you either increase the bevel angle this way by removing all this metal and regrinding a new surface and give the edge a new grind, or like I do, I have chisels designed for severing wood fiber, not human hair. I have them at about 20 degrees, about 30, 35 and 40, so I can pick and choose and match for the hardness of grain and the application. That's also why the real test of a chisel or any edged tool is not whether or not it could cut human hair, or whether or not it can slice through an automobile bumper. The real test of a tool is whether it can do what it was designed for, whether it can sever wood fiber, or if it's in case of a razor blade, whether it can cut hair, or if it's a splitting axe, whether it can split wood successfully. And this one can sure split wood, but it's just not designed for shaving. And if we go back to the previous page there for a sec, to calculate the angle on a composite blade which has two bevel faces is very similar to this calculation that we did. We are gonna need to chop up this blade like so into two pieces of right angle triangles, calculate one, and then double the result, and that's how we get the final answer. So what do I mean by double the result? Let me just show you on this splitting axe here. And just switch this one on. My first measurement will be this way, to measure the length of the bevel. Standard procedure, and it varies a little bit, but 8.5. It's a little longer there. 8.8, 8.4. We're gonna go with 8.5. Okay, guys. How about 8.5? That's a nice number for length of bevel. 8.5 millimeters. And I'm gonna need to take a second measurement somewhere around here at the top of the bevel. That's a little too much. So that somewhere there is looking nice. One side, I have to check it on the other side to make sure it's good. I'm just trying to tilt it so you can see the jaws on the caliper. Sorry guys. Oh, okay. 7.9. We're going to work with 7.93. And that measurement is again from here all the way down here, but we are only going to need half of it because we can only calculate one triangle, one right angle triangle at a time. So we're going to do this triangle. So the measurement was 7.93 millimeters from one face to the other face. We're going to need to divide it into two because we only have half of it for the triangle. 7.93 7.93 divided by 2 equals, and just one part there is 3.965. So let me just zoom in a little bit there. So that's gonna be sine second function bracket 3.965 divided by 8.5, and then whatever result we have, we're gonna have to double it because we have two of these triangles. So let's go second function sine bracket 3.965 divided by 8.5 equals 27 degrees of included angle for one triangle there, and then we double it, so we just go times 2 equals 55.6 degrees. Let's call it 56 degrees, okay? 56 degrees for a splitting axe. Let me just zoom out a little bit. So, ladies and gentlemen, this is why you can't shave with an axe. Its included bevel is 56 degrees. On a razor blade I took measurements, and let me just list the numbers. Where do I list the numbers? Here, razor. On a razor blade I took measurements, and according to my calculations, all razor blades have an approximately 10-degree angle, and it does cut hair. On this chisel we made a calculation, and it has a, well, we'll just call it a 20-degree angle, and it still cuts hair to some degree. I have chisels 30, 35 and 40-degree angles, and then this was chisel, 20, also 30, 35 and 40, because these angles work well with severing wood fiber along or across the grain. And then we have a splitting axe. Splitting axe, and it has an included angle of 56 degrees. It works wonderfully well when it comes to splitting wood fiber, but it miserably fails when it comes to trying to sever hair or cut paper with it or anything of that nature. So that's basically how and why you can't shave with an axe, no matter how sharp. Never will. Don't even try.